We finally arrived at the last lecture in our general chemistry module. We'll close this out with electrochemistry. The first thing we have to go into are some fundamentals when discussing the electrochemical cell. This describes any cell where an oxidation-reduction reaction takes place. It comprises of an anode and a cathode. Also, there generally is a salt bridge to make sure that the ion concentrations stay relatively even. Anodes are the oxidation site, and they attract anions. Cathodes are the reduction site, and they attract cations. A good way to remember this is anox, red cat. That's how I remember it anyway. So if you look at this example to your right, which one is being oxidized and which one is being reduced? Well, zinc is getting a positive charge, therefore it's got to be losing electrons. So if it's losing, Leo says losing electrons is an oxidation. So this has to be an anode, meaning that this has to be a cathode. And if we look, that would also be the case. Electrons always flow from anode to cathode, which would make sense. You lose electrons at the anode and you gain electrons at the cathode. There are different types of electrochemical cells. Here are the two most fundamental. The galvanic cell, or the voltaic cell, is a spontaneous reaction with a positive electromotive force. Since this happens spontaneously, it does not need any external energy to make it happen. An electrolytic cell, on the other hand, is non-spontaneous, therefore having a negative electromotive force. Why might we want to do this? Well, there's an industrial procedure called electrodeposition, which is where you plate something with another compound. If you have any sort of plated items, for example, computer parts or jewelry, it's often done by electrolytic means. The electrodeposition equation is listed below. It simply states that mole m, being the amount of metal ion being deposited on a specific electrode, equals current times time divided by the number of electron equivalents for a specific metal, and F, which is the Faraday constant. There are some other types of cells we should go into though, starting with a concentration cell. These are specialized galvanic cells that use concentration gradients to operate. And there are two types. The galvanic equivalent of a concentration cell has a negative charge anode and a positive charge cathode. An electrolytic concentration cell is the opposite. A rechargeable battery experiences charging, electrolytic, and discharging, galvanic. The battery in your cell phone operates on this principle. When it's plugged in and charging, it's going through an electrolytic process. And when it's discharging, when it's unplugged and you're going around your daily business with it, it's in a galvanic state, therefore discharging. We finished our discussion of electrolytic cells, so let's go into cell potential and how to calculate that. Cell potential is calculated via reduction potential, which is the tendency for a species to gain electrons. The standard reduction potential is how we calculate these, and the standard reduction potentials for each species under standard conditions has been calculated. If you need to use these on the MCAT, it'll generally be provided for you. Below is a table listing these. As you would guess, when it comes to reduction potentials, whichever one has the higher reduction potential is going to be the one that's being reduced, which is important when we're talking about calculating standard electromotive forces. This is the difference in reduction potential between two half cells. For a galvanic, it's going to have a positive electromotive force, and for an electrolytic, a negative. And this is calculated by taking the reduction potential of the cathode minus the reduction potential of the anode. The last thing we're going to go into in the lecture is Gibbs free energy. I'm sure you thought you escaped it and saw the last of it, but here it is again. There is an expression for Gibbs free energy that uses reduction potential, and that equation is listed below. The Nernst equation is also something that you're very often going to see on the MCAT. When conditions deviate from standard conditions, we have to use this equation, and as you can see, there is a Q as well. This is the same Q that we see in our equilibrium lecture, so just keep that in mind. In general, RT over NF can often be approximated to be 0.0592 over N, so you can use that approximation if you so desire. But if you do use that approximation, take into account that you're going to have to use log. So if you have to switch between natural log and log, this is a way to do it. There are different manipulations of Gibbs expressions. Below are the types of expressions you will see. Using the electromotive force, and the equilibrium constant, you can generate a lot of different types of relations that you would not otherwise have. Now, the one relation that we haven't really talked about when we're talking about Gibbs is this one. This is also an expression of Gibbs, but for equilibrium and electromotive force, this one's often not going to be used. As you can see, Gibbs has come up quite a few times in multiple lectures, which means it's very important for the MCAT, so I would strongly recommend that you have all these memorized. Alright, you guys just finished the general chemistry module. We will see you in the other modules.